Mars was a different world, warmer, wetter, and possibly alive. This is Jezero Crater, 49 kilometers wide. At its heart lies a river delta, a fan-shaped wedge of sediment that formed when water still ran freely across this surface. For millions of years, an ancient river fed a lake here, depositing layer after layer of silt, clay, and organic material. The reddish tone comes from iron oxide rust. These rocks are basaltic, volcanic in origin, erupted from the Martian interior long before the lake ever existed. Their angular, blocky shapes mean they have not been transported far. They broke where they sit, or close to it. In February 2021, NASA's Perseverance rover touched down precisely here. Its robotic arm carries instruments capable of identifying organic compounds that, on Earth, would point directly to life. These dark, finely layered rocks are among the most scientifically valuable formations in the crater. The lamination throws thin, repeating bands formed as the lake level rose and fell over thousands of years. Each band is a chapter, a different chemistry, a different season, a different climate. In some places, these stacked layers reach 60 meters thick. That is not erosion. That is time, preserved in stone. The crater floor is unusually flat, a product of long-term water pooling and sediment settling. That large fractured boulder did not fall here recently. It has sat in place through 3 billion years of freezing, thawing, and dust storms, slowly cracking apart under Martian stress. Every meter is documented with cameras, radar, and spectrometers. The rover is not just exploring, it is building a geological map detailed enough to tell scientists on Earth exactly where to drill. "200 meters per Martian day, or SOL. Sedimentary environments are where biosignatures tend to survive. Fine-grained lake sediments can trap and preserve organic molecules for billions of years, which is exactly why this delta was chosen as the landing site. The dark rocks scattered across the regolith here represent distinct phases of the lake's existence, each with potentially different chemistry. The name Jezero comes from South Slavic languages, where it simply means lake. It is an apt name. The crater was identified as a paleo lake decades before any rover ever landed here. The fracture patterns in these rocks reflect deep structural stress, likely from the same ancient impacts and tectonic shifts that shaped this entire region. Every scan adds data to a growing picture of what Jezero's lake was like, its temperature, its acidity, how long it persisted. This zone is one of the highest priority sampling areas in the entire mission. This material is over 3 billion years old, formed when Mars was still geologically active, still generating heat from its interior. Mars lacks active plate tectonics today, but early in its history, the crust was dynamic cracking, uplifting, and being reshaped by the same forces that still govern Earth through the atmospheric haze. When these samples eventually reach Earth laboratories, they will be subjected to mass spectrometry, isotope analysis, and electron microscopy techniques far beyond what any rover can carry. Three billion years ago, this entire surface was underwater. It is a geological archive written in stone. The contrast here is visually striking. The reddish, iron-rich regolith represents the surface as it exists today, oxidized and ancient. The darker, angular basalt fragments are remnants of Mars' volcanic past, chemically distinct and telling a different part of the story. The sediment layers visible here accumulated over what geologists estimate was at least 10 million years of active water flow, not a brief flood, but a sustained, potentially habitable environment. Ancient river channels carried material from the Martian highlands down into this depression. Martian dust storms can last for months and circle the entire planet. This debris field is the surface of Mars at its most honest, broken, oxidized, and ancient. These fragments are pieces of a crust that formed over 4 billion years ago and has been pulverized by impacts ever since. not looking for obvious signs of life, but for subtle chemical anomalies, elevated carbon ratios, unusual mineral phases, anything that deviates from what simple chemistry would predict. It is a record of Mars' long oxidation, the process by which water and atmosphere were slowly lost to space. What looks chaotic is actually the end result of slow, ordered physical processes.